So, jumping back into our lessons, where we left off before, we had started talking about rotational kinematics. So, rotational kinematics, that is a fun word. Let's break it up here. Rotational, something rotating, so the torques and such that we've been talking about up to now. And kinematics just means motion, okay? So it means rotational movement, okay? So rotational movement is really what we want to get into. We already talked about dynamics. We talked about, kinematics last semester. We talked about it in terms of our x equations. So when we wanted to know where something ended up, if something's traveling along, right, we want to know its final position, we had to know its initial position. We had to know how fast it was going, at least at the beginning, right? We had to have that initial velocity, and how much time had passed, and if there was any acceleration, if the thing started speeding up as it went. Then we also had to account for that acceleration. We did that with that 1/2 a t squared factor over here. And remember, t is your time, initial velocity, initial position, acceleration, and final position. So this was our first kinematics equation, all the way back beginning of last semester almost. So it turns out that rotationally there's an equivalent. The thing that we want to find out though is now how many degrees, or really, and we shouldn't be doing degrees, we should be doing radians, right? So how many radians have we gone through? So if we want to know how many radians we've gone through, think about what's going to happen here. If I have a wheel, and I want to know, in fact, let me draw a little point on here. I can do that. So let's get a little dot on our wheel. There it is. Okay, so if I want to know where that dot is going to end up after some time, where is it going to end? Well, we need to know where it starts, don't we? We need to know if it's at 0 radians or if it's at, I don't know, this is going to be 3 pi over 2 radians, is that right? Yeah, 3 pi over 2 radians. Or if it comes back to 0 at some later point, right? We need to know exactly where its starting place is. So, just like in our kinematics equation from last semester, we need to know its starting point. Here, we need to know this dot's starting point in terms of radians. How many radians does it start with? Well, if I start here, it's at 0. Here it would be pi over 2, pi, 3 pi over 2, and back to 0. Or a full 2 pi radians if you've gone through a revolution. So we need to know where it starts, and also how is that dot going to move? It's going to move with some speed, right? If it's going to move at all, it has to have some kind of a speed to it. So the way we're going to take that into account, before we talked about our speed or our velocity. So now we got to talk about a velocity again, but it's that rotational velocity, that little omega, right? We got to figure out what its angular velocity is. How fast is it going? How many radians is it sweeping out per second, right? And again, just like anything else, you have to figure out how much time is going to pass. So what velocity do you have and how much time? That'll tell you how many radians you're going to go through. So if that's all we have, is just a constant angular velocity, constant omega, then after 1 second, right, maybe we go through 2 pi radians, another second we get through another 2 pi radians, a third second we get through another 2 pi radians, and so on and so forth. But what if that wheel is accelerating? Our omega is actually changing. So to have our omega change, we have to have another factor as well. We have to have an angular acceleration, or an alpha. Okay? And just like the last term that we had here, you'll get a 1/2 alpha times squared. And the reason we get to this is weird. Why do we get the 1/2 and the squared? If you really want to know, it's all about calculus. This right here is actually the integral of another equation, an equation we're going to look at next. One that I think you'll remember, at least the outlines, the linear version of it that we had last semester. So if I want to know how many radians this little dot is going to go through, let me make sure I got the same time. Oh no, Dottie went away. There we go, Dottie. Okay, so here's our dot. Okay, so if I want to know where it's going to end up, I need to know where it starts. We're already at pi. Okay, we need to know how fast we're going and for how long. And we also need to know if we're accelerating and speeding that dot up as it goes. All of those things will affect our final radial position. Okay, so that's the first formula. The second formula, what if we don't care about the position so much, but we care about the speed of this object? How fast is it going in the end? That's what I really want to know. Okay, so last semester, put a dotted line here. So we got a whole new set of equations we're going to work with, okay? So if we want to know our position, there you go. Linear version, rotational. And you can see they're pretty much identical. We're just swapping a theta in for an x, an omega for a v, and an alpha for an a, right? These are all just the rotational version of that, okay? But if we want to know how fast we're going, our linear equation for velocity, if you remember last semester, final velocity, the velocity you end up with, well, it matters how fast you were going in the beginning, right? How fast am I going? How much do I accelerate as I go? So that other term has to be acceleration. And if you accelerate, it's got to be some amount of time that you accelerate for. The longer you accelerate for, the faster you're going to be going in the end. Well, for a wheel, same thing's true. If I have an initial speed, how do I speed it up? By accelerating. How much did I actually accelerate it? Well, I accelerated it from here to there, so it's a distance. And if I timed it, we could get an acceleration over time, see how much I'm actually speeding that dot up, which by now is probably a blur to you, okay? So, our final rotational speed should be the same thing as basically our velocity before. Our final omega, our final angular, or rotational, our final rotational speed, or angular velocity, has to be equal to wherever we started, however fast we were going at the beginning, plus any acceleration we had, and for how long it was accelerated. So in the end, you get these equations that look very similar to our equations from last semester. So go ahead, take a second to look at this. If you need to, you can review the video, write this down. I'm going to go ahead and erase it so that I can have some time to work here, or some space to work here. I'm going to start with the first equation. So let's talk about our position. Let's work a problem or two. All right? So, you can see this board works about as well as my whiteboard at school. It's amazing, right? So, there we go. Okay. So if I want to know where I'm going to end up, what position, what radial position, right? Where is this dot going to end up if I rotate it around? Well, if it's going at a speed already, right? Well, let's take this. It has no speed. Where's the dot going to end up? Where it began.